It's hard.
You're good. Do you have a question on the homework?
Yeah.
Okay, what's the question on the homework? Well, actually, let me just mention something before we get started. And if you could, can you do the course evaluation for this class? Just, it'd be very helpful, be honest. Say what works, doesn't work, that type of thing. And that's helpful, that's very helpful for future classes. I do look at it. And I'm not gonna be upset if you say bad things. Well, I'll be upset, but that's okay, don't worry about it. What's that?
You're glad the same pants you got mad in.
Exactly. It's not bad, it's good. It's good for me. Anyway, Salam, you got a question?
Like, for starters, this is 19.3.
And what's the question? I forgot.
Okay. Thank you, so. You have it? I have
19.3?
the big one.
Oh.
You got it? Oh, sweet, thank you. It says to cool a hot bath containing 50 liters of water at 50 degrees Celsius down to 20 degrees Celsius. And then it has questions.
Okay.
And then it says what volume of cold water at 5 degrees Celsius would be needed in liters.
To do what?
What volume, to cool a hot bath containing 50 liters of water at 50 degrees C down to 20, right?
So,
And then it's, yeah. Yeah. And then what volume of cold water at 5 degrees Celsius would be needed in liters?
5 degrees Celsius. Question.
And then the second question is what mass of ice at 0 degrees Celsius would be needed?
Okay, these are good ones. All right. Does it tell you the heat of fusion of
No.
the ice? It's probably in the chapter somewhere, right? Can somebody look that up, what the heat of fusion for ice is?
334.4.
Oh yeah, it's 333.
334.4, is that kilojoules per kilogram?
Mm-hmm.
So that's the same thing as joules per gram. Okay. Actually, I'll use kilojoules per kilogram since we're dealing with liters today. Okay, so we'll do this first one first. So we start out with 50 liters at 50 degrees C. And that's like what, about 125 degrees Fahrenheit, something like that, really hot. 120, yeah, something like that.
Just 112, 111.
No, that's 100, that's 45 degrees C. Yeah, when I got up to 113, I remember they made a big deal of it because it was 45 degrees C.
It's 122.
Okay, so what we need to do is we're going to consider the cold water that we add, one system, and this bath of water, a second system. And then we're going to look at the heat transfer between them. So just like what we did with iron, hot iron inside water. So I have this system here, and then I'm going to put the colder water. Maybe I'll make it a different color. And then the colder water here. Of course, it'll mix around, but I'll just say that I have a mass of cold water at 5 degrees C, and then this hot water at 50 degrees C.
So is this saying like the final temperature of both will be 20 degrees C?
Well, that's what'll happen if you mix it in, right? If you want to get that hot water to 20 degrees C, you have to, and you mix it, the final temperature of everything would be 20 degrees C.
Okay, I don't understand that.
Okay. So we have these two systems. I'll call this 1 and I'll call this 2. Okay, the heat going to 1 will be equal to the negative of the heat going to 2. This is our conservation of energy when we have two things in thermal contact and there's no work being done. The heat lost by one will be equal to the heat gained by the other. Q1 is the amount of heat that's going to 1. Q2 is the amount of heat going to 2. And so 2 will actually be losing heat. So that's where this negative sign comes in. Does that make sense? Okay. And if I add these together, I see Q1 plus Q2 is 0. The total amount of heat added to the whole system of both of them is going to be 0. Make sense? Okay, so that's where we'll start out with. And we know that, so Q1, for instance, would be the heat capacity, which is the mass times the specific heat of water times the final temperature minus the initial temperature. Final temperature would be 20 degrees C minus 5 degrees C. Okay? The Q1 or Q2 will be mass 2, which was 50 kilograms, right? Because each liter of water,
Oh,
a liter of water, what's the mass of a liter of water?
1 kilogram.
Yeah, a liter of water is 1,000 cubic centimeters. Each cubic centimeter of water weighs 1 gram. Okay, so 1,000 cubic centimeters, which is 1 liter, will weigh 1,000 grams or 1 kilogram. So I'm going to write this as 50 kilograms CH2O, and then the final 50 degrees C minus 20 degrees C, final minus initial, 50 degrees C. The CH2O, that was, what was it?
4.1.
It's
4.186,
4.186
yeah.
kilojoules per kilogram. Okay, that makes sense? So go ahead, plug that into here, and you figure out what Q2 is.
And then whatever, so it would give us the mass and then that's just converted into liters.
Yeah, that's right.
Okay.
Make sense?
Yeah, it makes sense.
Okay, and then the second thing, the mass of the ice you have to put in here. So we did heat of vaporization last time. Heat of fusion's a little different. We did do heat of vaporization, didn't we? And you boiled off all the steam, see how much heat we had to do. Heat of fusion's the same idea. If I have something that's frozen, even if it's at freezing temperature, I have to add heat to it to make it liquid at freezing temperature. Does that make sense? So it doesn't just naturally turn, it doesn't just, when it gets to freezing temperature, when it gets to that place where it can go from liquid or solid to liquid, it doesn't just automatically go to liquid without extra heat being added. You have to kind of break up the, the structure, the solid structure that it formed. And so, and the amount of heat you have to do to make it go from solid at freezing temperature to liquid at freezing temperature is this amount of heat. Does that make sense? Okay, so this is still the amount of heat that Q2 had to lose, right? And that will go into heating up that ice and making it liquid. So the amount of Q1 for the ice then is going to be mass of the ice times 4.4 kilojoules per kilogram plus, and then once I've melted the ice, it then has to heat up to the 20 degrees C, right? So mass seawater, mass of the ice, seawater, H2O. I say H2O, I mean liquid water. And then 20 degrees C minus 0 degrees. Okay. And so I take that, whatever heat I needed to here, and I'd say that that has to be added to the ice. And that ice has to finally get, turn to water and then finally get up. Was the ice at 0 degrees?
It didn't say. Did it say that?
Ice at 0 degrees.
Yeah.
Okay, good. You don't have to heat up the ice at all to get it to melting temperature. So the idea is that the heat that gets added to the ice would be the mass of the ice times however much it takes to melt that ice, every kilogram of ice. So that's this part. And then whatever ice is melted is now water, and then that has to heat up to that final temperature. And
So we're solving for the mass of the ice.
and then you go and solve for the mass of the ice, yeah.
Then we'll just get Q1. How do we get Q1?
Then Q1 is negative Q2, which you already calculated there.
Okay.
Okay? That makes sense to everyone? Just kind of look at where this heat has to go. It goes into melting the ice and then raising the temperature of the ice. And the temperature of the melted water and the original water should be the same in equilibrium.
Will those numbers be given to us, the 334.4 kilojoules per
Oh,
kilogram?
yeah.
Okay,
Yeah, there's no way I could, shoot, I have to look those up every time,
okay.
so. I think it's like 2,200 for the heat of vaporization for water, but it's something you have to look up.
Can you show us the algebra, like getting the mass of the ice by itself?
So that's mass of ice, times 334.4 kilojoules per kilogram, plus CH2O, 1 degree C. Okay?
Oh, you
It's just a number.
factored it out.
Of course, you can factor out.
Well, yeah, but that's at plus right there, though.
Well, yeah, cool.
Yeah.
Yeah.
Yeah, you can still factor it
So if I distribute this through, I get MH times this plus M times this. Okay, any other questions on the homework? All right. So I think that actually covered heat of fusion, which is the only last thing I really needed to cover for the homework, I think. Did I do anything with thermal expansion of solids or liquids? I think I left off those homework problems. I was trying to. Because I didn't really want to go into that. So today, what I would like to do is something that is, it happens in daily life. It's more or less for your own edification. Nothing will probably be tested on. Okay, and so don't worry too much about it. Just pay attention. Try not to fall asleep too much. If you do, and you start snoring, that's okay. I mean, leave the room when you start snoring, okay? So we're going to talk about second law, the second law of thermodynamics. Don't confuse it with Newton's second law, different. So the second law of thermodynamics. And this is always challenging because, but it's really deep stuff. And frankly, I think it's quite fascinating. There's a lot here. One thing I'd like you guys to think about is if I watched a movie, how would you know whether the movie was being played forwards or backwards? Just from the physics standpoint. what things would happen in a movie played forward that cannot happen played backwards.
Like stuff
Did-
falling, like if it's raining or something.
Well, I mean, you could be, so the droplets are speeding up going down, well, you could have it play it backwards at faster slowing up, down as it goes up, that's okay. So, I mean, there's a lot of things, you know, falling bodies are fine played backwards, you know, or forwards. You know, if I bounce a bouncy ball off the ground, it makes sense.
Making the sun come up in the western movies would be a little interesting, but it's a movie. It might not be heard.
Well, yeah, you know, physically that's potentially possible, you know, there's a Superman movie where they stop it and turn the earth around and somehow that makes time go backwards, which doesn't make any sense. But, you know, there are things like that. The things that do not happen, if I move my hand at a constant speed over here, I'm heating up the table and it's making my hand hot. And my movement is going into making the table hot. Does that make sense? It would never ever work in the opposite direction, that the hotter table in one little spot here would make my hand move in a particular direction. That turns out to be what is not possible if you look backward, reverse the film and look backwards at it. Those types of things where you involve what we call irreversible processes involving heat transfer. And the reason is that there's one fundamental principle that determines the direction of the evolution of the universe, and that's entropy. The increase in we'll deal with that in just a second. But heat only flows from high temperature to cold temperature. It never flows the opposite way, spontaneously. And that's the fundamental thing that puts a direction on time, strangely enough. All the basic other laws of physics, if I play the tape backwards or forwards, it would obey it both ways. So it's kind of an interesting thing that's what it is. And so we're going to go take a look at kind of the details of a particular problem, and hopefully we'll get to look at a situation where we can understand the efficiency of engines. This is where the original idea of entropy came from, and this is still probably one of the more interesting examples and the easiest one to get your head around. So we're probably going to have to get into details here. Okay, make sense? All right. The first thing is, let's understand kind of the basic flow diagram of what an engine is. So an engine takes heat at one temperature, usually a higher temperature. Heat flows from a higher temperature to the system or the engine. I'm just going to call that S, or the system. This is the thing that does work. I'm going to call this Q2. And then the engine, after it does some work, gives off whatever heat's left over to a system, to a lower temperature, not a system, but something at a lower temperature. Q1. And the amount of heat going from the hotter temperature to the system, I'm going to call Q2. And the amount of heat going from the system to T1, I'm going to call Q1. T2 is bigger than T1. That's the basic idea behind how to do work with heat. And all engines tend to actually turn out to be based on that principle. So if we have a gasoline engine, for instance, we burn the gas, make it hot and expand the gas. We added heat to the system during the burning process. And then we have to give off heat to the environment, and that makes, and then we go back and keep doing that. And that's the principle behind the gasoline engine. If you're talking about a steam engine, you have hot temperature boiler with hot temperature, whatever the temperature of that steam is, a piston, and then you have the environment at the colder temperature. Okay? So this colder temperature for most engines turns out to be environment temperature. Whatever the temperature is outside of the engine. Okay. So let's kind of get into the details of how one might construct a piston engine. And we're going to look at the most efficient type of engine. So there's a rule, and this is something that I won't prove, but the most efficient engine is the one where there's nothing done in the engine besides work. Engine where nothing is done but work. And so what this means is that if I looked here, the only thing coming out of the engine, the only output, we'll say, is the work done by the engine. And if this holds, then we can say that Q2, the amount of heat entering the engine, minus Q1, the amount of heat leaving the engine, would equal W, the amount of work done by the engine. Okay? Or the amount of heat added to the engine is equal to the work done by the engine plus the heat leaving the engine. So there's nothing besides good work being done and then heat given to the environment. This would happen pretty much in any engine, but the most efficient one is engine is one where nothing's done but work, and it is reversible. So what do I mean by a reversible engine? Well, let me kind of give an example. Let's say we'll look at one reversible process. Let's say I have a cylinder and a piston where the whole thing's kind of insulated, except at the bottom, where this gets attached to some temperature T2. Okay. There's something held at temperature T2 at the bottom of this cylinder, and let's just say that this is T2 to begin with. Okay. If I start moving this piston upwards, this gas would want to cool, right? Because what I'm doing is I'm increasing volume. Wait. Well, what I'm doing is if I just had this gas isolated and no temperature there, I would be doing work by moving this upwards. And then the energy of the gas itself would have to be going down. And we know that the change in energy of a gas is 3/2 K times the change in temperature for an ideal gas. F. Number of gas molecules, NK delta T. So if I'm doing work, I'm lowering this energy, and therefore I'm lowering the temperature. But if I have it on top of this temperature and I'm holding the temperature fixed, what instead will happen is as soon as this temperature lowers infinitesimally, then this is bigger than this temperature and heat will flow. Does that make sense? So I start to get heat flowing to the cylinder when I start to do work here. If I do this very, very slowly, I'll just get the heat flowing from T2 into the cylinder that's equal to the work that I get out here. Does that make sense? So in this case, the work done would be equal to Q2. Now, a reversible process is one that would be okay to do it the opposite way. A reversible process is one where if I have these initially at the same temperatures, T2 and T2, and I start pressing it down after it has expanded, you know, as I compress this gas, it wants to heat up a little bit. And then as this temperature gets a little bit above T2, heat flows backwards into Q2. Does that make sense? So heat flows backwards, Q2 going this way. Well, the heat just flows this way, okay? A reversible process is one where I get the same amount, where if I do the work going upwards and using Q2, and then press it back to its initial position, that the same amount of heat would flow back into this. And there would be no change in the system, no heat loss to the environment, no movement of the gas in here, nothing like that. And it turns out that a reversible system is the most efficient engine. We won't prove that. That just is, that's more or less experimentally demonstrated many, many times. That the closer you get to reversible engine, the more efficient you have it. Okay, in fact, another statement of the second law, which says heat flows spontaneously from high temperature to low temperature. You can also say that it's an equivalent thing is to say that the reversible engine is the most efficient engine, but we won't go into that quite. Okay, so let's look at how we have an engine between two different temperatures. Now, an engine has to work in a cycle. If I have a single piston, after a cycle of the engine, I need to have it back to where it started. You don't want the engine to be constantly changing as it goes on. So the engine has to come back to its initial position. That's what we'll call an engine, or a cycle. So how can we do that between two different temperature sources and do it in a way where it's reversible? So let me go through and illustrate the way that this is done. And there's only one way to do this. So things are reversible if we're having heat flow between the same temperature, like in this process. This is called an isothermal process. ISO means same thermal temperature, so this is the same temperature. And you'll notice we had to have the T2 and the reservoir, the heat reservoir, the heat here, the temperature T2 here, and the temperature of the piston were the same. And so that's why we could have the heat flow in if we raise this, and flow back out if we make it go down. Because the heat, if it's the same temperature, any little change will make the heat flow one direction or the other. If these weren't the same temperature, say this is significantly hotter than that, then if I pressure this down a little bit, heat won't flow back into this thing, because heat will only flow from the high temperature to the low temperature. would still be flowing into it if this was, even if I started pressurizing a little bit. So you cannot have so the reversible process can happen with isothermal processes. It can. Where we have the piston and the temperature being the same. It can also happen in what we'll call fully insulated or adiabatic processes, is another term. So a different process. This is called adiabatic. And basically it means insulated.
So does that mean the heat is equal to 0? Like there's no change in heat?
That's right, no change in heat. So you can imagine a cylinder with completely insulated walls. You know, think of it as a dewar. Completely insulated bottom and have a piston up here. And if I press on the piston here, this thing might heat up because I do work on it. But then if I let it go, it just goes right back to you. And that's also a fully reversible process, provided I do it fairly slow. So this is also reversible. Okay. And it turns out that the only way to add heat to the system reversibly is with isothermal processes, and the only other type of process that is reversible are adiabatics, or adiabatic processes, and that's it. Those are the only things that you can do with cylinders that tend to be reversible.
What do they call it, adiabatic heating of the winds?
Oh yeah, that's where like for instance, we assume a column of air and stuff like that going upwards, that air is such a good insulator, any little column that's going upwards and transfer heat to the surrounding air. So yeah.
Comes the mountains, it dries out, drops down, and warms up.
Those are the Chinook winds, right?
Chinooks, Phillips, it's part of adiabatic.
Yeah, that's why they do it, because it's insulated. We're assuming the air is not transferring heat to be having heat transferred to it. Okay. Anyway, let's go ahead and see how we can construct a full cycle with these two processes. And that'll give us our reversible engine, and then we can figure out the efficiency of it. Okay. I'll have to erase this. Okay, so we'll draw a little picture. These walls of this cylinder are insulated. We have a piston here. And I won't draw this, it's just a piston, okay? And then I have a gas inside of here. The first thing you do is you get the gas to whatever the T2 temperature is, and you put it in contact with T2. Then start to raise this. Raise the piston a distance X. Okay? And in this case, the volume changed by the gas is delta V is right up here. The amount of work done by the piston will be P delta V. P is actually changing during this process, so you have to adjust this slightly. But for if it's a small x, it's about that. And then heat absorbed in this process, Q2. As I increase this, I'm actually getting heat to absorb as I raise this. will be equal to the work done. So what you then have is you have a system that is at a bigger volume, same temperature as it started out with, some work was done. If I were to draw that on a pressure and volume diagram here, start out at the lower volume. What I did was I started out at a volume, I increased the volume. Pressure actually decreases. We did it all at the same temperature. So you get something that looks like this. So I'm going to call this step 1. And we'll say we increase it to volume 2, V2 minus V1 is equal to delta V. And this is all done at one temperature, T2. Let me write the T2 right here. This is called an isotherm on the PV diagram. The slope, the shape of this is, well, we'll worry about that in a little bit. But if it's all at a constant temperature, we know that PV equals nKT. So if this is a constant, you know, P would go like NK over TV, with P is equal, which goes like a constant over volume. Make sense? So it kind of, this is like 1 over volume here. Okay, now you're at a bigger volume, same temperature T2, and you've done some work. We want to now then make it so that this thing gets to a different temperature T1, where I can give off some of the heat that it gains. T1 is lower than T2. So how would I get that to a lower temperature T2 now? Compressing it'll heat it up, won't it?
Oh yeah, it will. Expanding.
Expand it even further, and then it'll lower its temperature. So if I expand it even further, it does work. And as it does work, the energy of the gas lost energy and its temperature decreased. So what I do now is I take away this temperature 2 source, make the whole piston insulated. Make the whole cylinder insulated. So this is step 2. This is 1. Step 2. Make the whole cylinder insulated. Whole piston insulated. It's at its bigger volume, T2. And then what I do is I raise it even further. And as I raise it even further, increasing the volume, I lower the temperature because I did more work. The gas lost some energy. The lowered its temperature. So if I were to draw this process here, it increases its volume further and the temperature lowers. The pressure lowered too inside there, and it actually is fairly steep. This is called an adiabat, and it's steeper than the isotherm on the PV diagram. All right, now I'm at the lower temperature, T1. So that's turned into T1 at the end. I adiabatically increased it till the temperature lowered to T1. So I've done work. I'm at temperature T1. I want to go make it give off some of the heat that it gained back to its lower at the lower temperature. So what I do is I have T1 now. I put this in contact of the lower temperature T1. This is insulated. And then I have to reversibly compress it. So compress it slowly. As you compress it slowly, it gives off heat, Q1, back to that temperature. So I compress it now. This cylinder's not doing work. Work has to be done on it to make this happen. But as it compresses, it gives off heat back to T1. And it ends up with a, and as that occurs, its volume, it goes back up like this, you know. This is T1, and the system goes back to smaller volume, slightly higher pressure. And then to get back to its initial position, this was 3, step 3. And then to get back to its initial temperature T2, I insulate it again on the bottom, and I adiabatically compress it. So all these walls are insulated. Move it further. T1 goes to T2. So if I do that on the PV diagram, it goes back up to here. Okay, and I get back to the final position, to the initial starting point. All of these processes were reversible because I was only adding heat when the two temperatures were the same, and so I could go backwards and make it give off heat without any trouble. Or I'm doing it adiabatically, where everything's insulated, no heat transfer at all. So everything is reversible in this process. This is a reversible engine. It turns out to be the only type, in principle, the only type of reversible engine. You could do similar type things with electrical work and whatnot, but for gas piston, this is the first reversible engine. And it has a name for it. Anyone know it? Chemistry, you might have heard of this, Carnot cycle. Anyone heard of that? Okay. So a statement of the second law of thermodynamics is that the Carnot cycle is the most efficient engine. And all reversible engines have the same efficiency. We can calculate the efficiency. We say that the efficiency of an engine, and I'm almost done, has a term eta. It is equal to the work done by the engine divided by the heat absorbed at the higher temperature. For a reversible engine, well, for an engine where, well, really any engine, by conservation of energy, the work done by it would be equal to the heat absorbed by it minus the heat given off by it. This is what we call the efficiency of the engine. For the Carnot cycle, we can see where the heat comes in and where the heat goes off. During these adiabatic times, 2 and 4, there's no heat transfer, so we don't have to worry about those. Over here, at the isothermal ones, the work done is the same as the heat transferred in. So I just have to figure out what this P delta V is. Well, it turns out that this P delta V, when I actually take into account that P is changing as V is changing, do a careful thing. Turns out that the work done is equal, and let me, I calculated this a little bit. For an ideal gas, well, for an ideal gas, it's actually NKT, natural log of the V final over V initial. We don't have to worry about this. What we can say is that it's just AT, okay, proportional to temperature. Here, the work done here is also proportional to temperature. And it turns out that the constant proportionality is the same, and I get A T2 minus A T1 over A T2, which is T2 minus T1 over T2. So, really quick, for a car engine operating at burning at 600 Kelvin, so the pistons, the cylinders are at, over, 330 Celsius. And the environment pressure, the environmental temperature, is 300 Kelvin. The efficiency would be 600 Kelvin minus 300 Kelvin divided by 600 Kelvin, which is 1/2. That's the maximum possible efficiency. That means half of the energy taken in the form of heat by the burning can be used to actually do work. Okay. Real engines, you don't get up anywhere close to there, you're more like 20%. All right, I'll let you go. Yeah.
What are the units for efficiency?
For efficiency, well, it's a ratio of the temperature over temperature. Ratio of the heat over heat.
But I would keep it, yeah.
Well, they're more efficient, better mileage, yeah.
Whatever you need, like it's
Of course, if you have it more for a given displacement, power is be better mileage.
Yeah, let's do it. I was like, I might go later.
Of course, what happens is all your torques, all your power is lower.
That might not, that would be a little much.
Bang, yeah, Dodge power line with the gas. No, that thing's
Well, I guess the worst is that in a diesel, it's hard to accelerate when you're at like from 50 to 70 miles an hour. That's like a bad time to accelerate in a diesel. That's a good time to gasoline engine.
I've always got to kick out the figures they use to sell the thing. And what it would be. Before it turned around and did.
A bunch of vacation destinations like that do like mass water burger or the side of my face. I ate like half of it, maybe.
I'm not sure.